Today I would like to derive Poynting's vector for the energy contained within electromagnetic fields. In order to derive Poynting's vector, we first consider a box of volume V. Inside the box there is an electromagnetic field which has an energy density of U, so that the energy inside the box is simply the integral of U dV. Poynting's vector concerns itself with the energy change inside this box. We denote S as the flux or flow of energy. From the conservation of energy we know that energy is only lost inside the box when S flows through one of the 6 sides of the box, or when there is work done inside the box. Therefore our conservation of energy equation becomes minus d by dt of the integral of u dv is equal to the integral of S dot n dA plus any work done inside the box per unit time. This highlighted integral here represents energy which flows outside of the box through one of the 6 sides. We rewrite the energy equation as minus d by dt of the integral of u dv is equal to the integral of div s dv plus the integral of the work done. Here we have used Gauss's divergence theorem to change the surface integral of S into a volume integral. Finally, we remove the integrals from the left-hand side and the right-hand side of the equation, leaving us with the energy equation in differential form as minus d by dt of u is equal to div S plus the work done. We now wish to calculate the work done per second. In order to do this, we must first understand the forces acting inside the box on a charged particle. A charged particle moving inside this box would suffer a Lorentz force, which is equal to F equals Q into E plus V cross B, where V is the velocity of the charged particle. We are now able to calculate the work done inside the box in terms of the electric field and magnetic field through the relationship that work is equal to force times distance. Thus we have the work W is equal to the integral of F dot dx, which is equal to F times x. Next, we write the work explicitly in terms of the Lorentz force, which is equal to Q into E plus V cross B dot x. In order to get the work done per second, we differentiate the left-hand side and the right-hand side with respect to time, leaving us with the W by dt is equal to Q into E plus V cross B dot V. We then expand the bracket on the right-hand side, leaving Q E dot V plus Q times V cross B dot V. The vector resulting from the cross product of the velocity and the magnetic field is perpendicular to the velocity. Therefore, when taking the dot product of the velocity with this resultant vector, it is 0. This is a very interesting result. The physical interpretation of the result is this. A magnetic field cannot increase the kinetic energy of a charged particle. That is to say, when a charged particle is moving in a magnetic field, it will not increase in velocity. The magnetic field has only the ability to redirect the charged particle without actually increasing its velocity. Thus our equation becomes dw by dt is equal to q E dot v, which is equal to E dot j, as velocity times charge is the definition of current density. Therefore, returning to our conservation of energy equation from before, we have minus du by dt is equal to div S plus E dot j. We now wish to express the current density in terms of the field vectors E and B. In order to achieve this, we use Maxwell's fourth equation, which states that the curl of H is equal to J, the current density, plus d by dt of D. The vector D is the electric field intensity vector. It is equal to epsilon E plus P, where P is the polarization of the medium that the electromagnetic wave is traveling in. For this derivation of Poynting's vector, we assume that the electromagnetic wave is traveling in free space, therefore the polarization vector is equal to 0. This leaves us with the vector D being equal to epsilon 0 times E, where epsilon 0 is the permittivity of free space. By substituting the above value of D into Maxwell's fourth equation, we have that the curl of H is equal to J plus epsilon 0 d by dt of E, where H is the magnetic field intensity. We wish to convert the magnetic field intensity in this equation to the magnetic field. We do this using the relation B is equal to mu naught H. Substituting the expression for the magnetic field into Maxwell's fourth equation yields that the curl of B is equal to mu naught J plus epsilon naught mu naught d by dt of E. We use the identity for an electromagnetic wave traveling through free space that c squared is equal to 1 over epsilon 0 mu 0. I hope to prove this relation in a later video on wave propagation in free space. We next multiply Maxwell's fourth equation by c squared, yielding c squared curl of B is equal to J divided by epsilon 0 plus d by dt of E. We can now express the current density J explicitly in terms of the electric field and the magnetic field. It is equal to epsilon 0 c squared curl of B minus epsilon 0 d by dt of E. With this expression for J, we could now express the mechanical work done inside this box explicitly in terms of the magnetic field and the electric field. Thus, the expression for the work before E dot J becomes E dot epsilon 0 c squared curl of B minus epsilon 0 d by dt of E. We now have an expression for the work done inside the box in terms of the fields E and B, and in the next video I will use this expression to finish off the derivation for Poynting's vector.